On August 14, 2019, the LIGO-Virgo Collaboration, LVC, detected the gravitational wave spawned by a possible neutron star Blackhole Merger, a rare event which was later designated as GW190814 by the LVC team. An extensive search for an optical counterpart of Kilonova was undertaken by the Dark Energy Survey Gravitation Wave team using two instruments located in the Chilean Andes, the DCAM imaging camera on the Blanca 4-meter telescope and the Goodman spectrograph on the SOAR 4-meter telescope. Douglas will describe the LVC detection of GW190814 and the DES as GW team's search for its optical counterpart, the results of the search and the lessons learned for optical follow-up of future LVC gravitational wave detections. Douglas was born in Florida in the mid-1960s. Some of his earliest memories were of the televised news reports of the Apollo moon landings. He became an avid amateur astronomer in middle school, devouring astronomy books during summer vacations. In college, he majored in physics and built a Dobsonian 10-inch telescope for an independent studies project. He obtained his PhD in astronomy at Yale, studying the clustering of galaxies in the Campana's redshift survey. He then spent 2 years as a postdoctoral researcher in Germany at the Astrophysical Institute of Potsdam. Afterwards, he moved to Aurora and joined Fermilab's experimental astrophysics group, where he has worked on the photometric calibrations of the Sloan Digital Sky Survey and more recently in the Dark Energy Survey. He is currently the Calibrations Scientist for the Dark Energy Survey. Please welcome Douglas Tucker.
Oh, thank you. This here. Okay, thanks. Okay. Well, thank you. Thank you, Kurt. Thank you, everyone. So I'm actually doing this a dual mode sort of thing here because I'll be. I'm also doing a Zoom session for others who couldn't make it here tonight. And so I'll be kind of, I might be a little bit distracted. So let's see. So yes, I was talking about GW 190814, the Kilonova that wasn't. So I'm Douglas Tucker. My wife here is Sahar Alam. She's also involved with this, also was heavily involved with this project. Let's see, move on to the next slide. I kind of go back and forth a bit. So I wanted to kind of cover, I want to give you somewhat of an outline, do some background on gravitational waves and gravitational wave detectors, on binary black hole mergers and binary neutron star mergers. Then talk about the first binary neutron star merger, which has a similar telephone number. It's 170817, about 2 years before the main one that we'll talk about, and talk about its detection by gravitational waves and doing follow-up with optical and near-infrared imaging and spectroscopy. And then I'll talk a bit about the main topic of this presentation, GW 190814, which is there's still some debate about whether it was actually truly a neutron star black hole pair or maybe it was something a little bit different. But I'll talk about the preparations for its optical and near-infrared follow-up, the actual detection by LIGO, the imaging and spectroscopy that we then did. So let's see. Okay, so first the background. So, oops, just gonna jump a slide here. Oh, no. Here. Gravitational waves. So what are gravitational waves? So these were gravitational waves were predicted by Einstein about a century ago. And they're sort of, it's basically if you have, say, two compact masses spinning around each other, they will output ripples in space-time. And so here's an example of two compact objects spiraling around each other and merging. And as they spiral around each other, they emit gravitational waves, so energy leaves the system, so they end up spiraling into each other and merging. And these could be like two black holes or two neutron stars, or a black hole and a neutron star, or basically any compact object like that. So how do we detect gravitational waves? So here are two of the first major detectors, observatories for gravitational waves. One at Hanford, Washington, and another one in Livingston, Louisiana. And so they have these two long perpendicular arms, about 4 kilometers long each, at right angles to each other. And that is because they are basically what are called Michelson interferometers. So how do these things work? So you have ripples going through space-time. They affect the lengths of things. They're very small, very minor. They're very hard to detect because they're not big events. At least they don't cause a lot of signal. So Michelson interferometer is if you have a laser, something which outputs coherent light, and you aim it to basically a partially silvered mirror, and some of the light goes through the mirror and bounces back. Some of the light gets reflected up to another mirror and bounces back. And with lasers, they're coherent light, so the waveforms go with each other. But if the waveforms get out of order, then you get what's called destructive interference. If the two lengths are exactly the same, the light goes the same distance and they stay coherent, and you have a positive correlation. You get a bright spot, you get a bright signal. You get, but if they're 180 degrees out of phase with each other, they cancel each other out. You get dark. So you can measure things basically on the order of the width of the wavelength of light, or better. So you have a gravitational wave that moves through here. It's first of all set up so things are just like one wavelength, 1/2 wavelength out, so they don't show anything at the detector. But if a wave comes through here, it's like you're out on the ocean or something, and things wave through, and the size will slightly change in one direction, then in the other direction, and you get destructive interference, and you get dark. Or actually, it moves into coherence at the detector, and you get a light spot. So that's basically how these gravitational wave detectors work. And not doing so well for the people online. Things are getting out of order here. Let's see. Moving on. So these two detectors are separated by about 3,000 kilometers, which is about 10 microseconds apart for light travel time in a vacuum, or gravitational waves move also at the speed of light. So if the gravitational waves hit here first, it'll be 10 milliseconds later before they hit there, or vice versa. And that actually helps you determine where in the sky the merger occurred. If the merger occurred way off in the direction south of Florida somewhere, or and it hits Louisiana first, and then 10 milliseconds later Washington, you know that the gravitational wave source is somewhere over there. If it stops it, it's over here. And you can do various convolutions to figure out if it's coming in this direction or that direction. Let's see, moving on. But you don't get a really great idea, especially with just two detectors. So here is a picture of the southern sky looking up. There's the Milky Way galaxy. There's the large and small Magellanic Cloud. And here is the what's called the localization contours for a gravitational wave event that occurred on December 26, 2015. So with the two detectors going, they could get a rough, it's like two areas of the sky, and you kind of take the intersection of that, and you get, it happened somewhere along this long strip. That's not very easy, helpful for trying to follow it up with other telescopes, but it at least gives you an idea where things are. The more detectors you have more. The more detectors you have, the more time differences you can measure from different directions on the globe, the better you can localize. And things have improved substantially with there's a third detector going on. Oh, there's a third detector now called Virgo near Pisa, Italy. That helps a lot. What else can they tell you? Okay, this is a little bit. Don't worry about these technical plots. But basically, each. So this is the signal that you get from the weight from the movement of the bars of the legs of each of the detector. The one in Washington and one in Louisiana, and you get sort of a squiggly thing, and then the amplitude increases, and then it decreases once things merge. So things are inspiraling. Especially right here, this the merger occurs here, and then it kind of stops. And the other thing is, the shapes are the same, which is good. That means that you didn't. It's not just a freak incident. So it's a real. It's going to be a real incident, and if you shift it by the appropriate 10 microseconds, they fall onto each other very well. That's good. You can also, the shape of this, and this is beyond me. I'm not in LIGO. I use the results of LIGO, but I'm not in LIGO. I don't know the whole details. But you can basically, you can simulate lots of different types of ways of different sizes of black holes or neutron stars and various parameters that you can compare what you'd expect. You have a whole long list of signals that you might expect, and you can compare them. You can do this very quickly with a computer and compare it and basically fit the best match to the observed. And in this and you can get, and also how large in the vertical direction, the larger the scale of the changes implies how close the object is to. So various information here. You can, in this particular case, this is the first LIGO detection ever, gravitational detection ever. It was on September 14th, 2015. It was, the results indicate there was two black holes, one that was 30.6 times the mass of the sun, and one that was 35.6 times the mass of the sun. And they merged, and they resulted in a black hole that was 63.1 times the mass of the sun. You also notice that 30.6 plus 35.6 does not adds up to something slightly higher than 63.1. So it's 66.2, and that extra 3.1 solar masses, all that energy went into gravitational waves and it sprayed out to the universe, and that's what we detected. Well, not we, but the LIGO folks detected here. You can also, and they also roughly estimate, it's a very rough estimate, that this object was about 440 megaparsecs away. I'll tell you these parsecs and megaparsecs a lot. To convert to light years, it's roughly multiplied by a factor of 3. So 440 million parsecs is roughly 1,400 billion light years, 1.4 billion light years away. Let's see. Let's see. Moving on. So actually, this detection and the whole LIGO experiment, well, that was that yielded a Nobel Prize in Physics for the leads of the LIGO team. So Rainer Weiss, Barry Barish, and Kip Thorne. Useful on today is there was the physics prize was announced for 2021 on climate change and structured systems. for physics. Let's see, moving on. Oops. Let's see. Let's go back here. Okay, so these are black holes. What about that what we saw before was for this object, this first black hole pair that was detected, and so that was basically a kind of cleaned up version of what we saw on the previous slide. Here are signals from 3 other black hole pairs. So so there's some differences, and it depends on the size of the black holes and various things. But what if you had 2 neutron stars merging? And so if you get 2 neutron stars merging, you get, okay, it's actually, the signal goes much, much longer, by like an order of magnitude or more, to the final flip at the end. So the other ones are like a second or so, a few seconds of a signal, and then of the in spiral and merger, whereas for the neutron stars, it takes quite a bit longer, at least on these scales. Okay, let's see, moving on. Oh, okay, now, what about, well, if you want to look at you get the waves, or if you want to look at a black hole merger by eye or something. Now, here's a simulation, and it's showing the background, the galaxy background, and light is being bent, so you're getting the lensing effects around these 2 black holes that are merging. None of that light is actually coming from the black hole system itself. It's all behind. I'm actually going to redo that. Oops. Wait, back. Okay. So none of this light is actually part of the black hole system, and it's actually believed in general that there's no accretion disks around these black holes. When you do have 2 black holes merging, like 2 similar black holes merging, you're not going to get any optical or electromagnetic effects. You'll just get the gravitational wave. But it's still interesting to kind of search in case there is. That could be wrong. On the other hand, for neutron stars, let's see. That's a lot. Here's 2 neutron stars, and they're shedding gravitational waves, which and they in spiral in. You don't actually see the gravitational waves, but they kind of but just for the simulation, it shows the gravitational waves being shown off. All of this is actually, let me rerun this. I can do that. Let's see. So what you get here is there's in spiraling these 2 neutron stars, and then they merge, and then first you get a big flash along the polar axis. That's gamma rays hitting material in the area. That's gamma rays. Then this is what's called the kilonova. This is a bunch of neutron-rich material from the neutron star, and it's very hot, expanding at about 1/10 the speed of light from the debris. Then you get some final remains as the gamma rays hit other material and produce X-rays. So that's that is so first get the two neutrons in spiraling. You get the gamma rays. You get light. You get optical and near infrared light from this part of the explosion, and this is kind of the final X-rays released along the polar axis. That's supposed to take about, the simulation covers about 9 days for this neutron star pair, this simulation. All right, let's move on. So we see that gravitational wave detectors are very good at identifying merging contact objects at large distances. These are millions of light years away, but via their gravitational waves. You saw that binary neutron stars, two neutron stars that are merging, they will produce an electromagnetic afterglow or explosion you can see with optical or infrared or gamma ray observatories. Black hole mergers, those also, but it's not likely that they'll have a optical counterpart, an afterglow afterwards. And then you might have like a mixed pair, neutron star, black hole. And there, you don't really know. It could have a afterglow, could have a Kilonova-like explosion or not. And then you can also measure the distances to these mergers from to some extent from their gravitational waves. But they're less good at localizing the merger event on the sky. Here's a all-sky, let's call it an ITOF projection. You know, you've seen pictures of maps of the globe, two-dimensional maps of full Earth. This is sort of like that. So this is the full sky, and here's localization for another black hole merger. And so you have a long stripe here, a one here. And it's about 1,000 square degrees. That's a lot of area to try to cover. And these things fade very quickly. So it's hard to get telescope time to try to cover that much area. And you also can't measure, and also although the gravitational wave detectors can measure the distance, they don't know what the recessional velocity is. And that's kind of interesting for if you're interested in studying Hubble, Lemaitre law sort of things, how the universe is expanding versus over time. We don't really get into that here, but just wanted to mention. Let's see, but this is good for. But the things that can do that are using optical or infrared telescopes for imaging, and for spectroscopy to identify the object optically, and also do follow-up studies. So a group that Sahar and I are in are the Dark Energy Survey Gravitational Wave Team. And we do imaging follow-up, and we're kind of minor actors here. Scientist Marceli Santos is one of the leads on this. But we've helped out, but Sahar and I helped out a bit, on this. So for optical follow-up for imaging, we use the 4-meter telescope, which is in Chile. Here's a picture of the Blanca 4-meter telescope. And the DCAM camera is this whole big apparatus here. And it has for research-grade telescopes, it has a huge field of view. It has a 3 square degree field of view, which for research telescopes is big, very big. And a 570 megapixel camera. And it has 60 science CCDs, which are currently working, which are optimized for the red part of the for redder things, so more appropriate for distant objects, which are with cosmological redshift, they tend to get reddened. And it also has very good resolution. You can resolve stars very well. So it's pretty much an ideal instrument, survey instrument for hunting down things like this. Let's see. Sorry, people online. Let me adjust that. Okay. And here's actually one of the first images from DCAM. It was mounted on the Blanca Telescope as you can see the spaces between the CCDs. But there's 62 working CCDs. It's 8 at the Fornax galaxy cluster. You can see nice spiral galaxies and other galaxies and so on. And for comparison, that's the moon, the full moon to scale. So it covers a nice area of sky. Okay. Now let's get back to this binary neutron star that we saw earlier. So there's a detection by LIGO, the gravitational waves were detected. So what happened there for optical follow-up? Well, first of all, they alerted the astronomical community basically by email, sending out messages via what are called GCN circulars. So on August 17th, 2017, at about 2 in the afternoon Greenwich Mean Time, it sent out a message saying, "We think we see something here," and the chance that it's a fake, that it's just some accidental measurement, is they measure their students and how often you'd expect such a thing to happen per unit time. And they said they estimated like this has a 1 chance in every 10,000 years of this just being an error in the data. So they provide information, and astronomers throughout the world started to move quickly. So also we, with Dark Energy Survey, did too. And so the localization region was okay, here's sort of one of those maps again in the background. Here's the Milky Way. Here's, I think that's a Large Magellanic Cloud. This was actually a fairly small area, which was very nice. So it's the little ellipse is the area that was provided by LIGO as being the likely spot for it. And these red hexes, these red marks are the pointings for the dark energy camera, the DCAM. So it only took a handful to cover the whole region, which is really nice. I myself was pretty oblivious to this. This was the weekend before the big solar eclipse a few years ago, and I was thinking about that, and Sarah said she got a word from the lead, Marceli Suarez Santos, that, "Oh, could we observe for this tonight?" And I said, "Oh, well, okay, we're going traveling to go see the eclipse, but okay." But anyway, so we were able to run the camera of the telescope from Fermilab, so we'd have to go travel to Chile in a few hours. So that very evening, we went and set things up running, and we had to go quickly because this area of the sky was just was going to set in about after sunset. It sets within about an hour or so, after an hour and a half after sunset. You have to do it quickly. It's setting quickly. So we started observing as soon as it got dark in Chile. And this is about 10.5 hours after the merger occurred. And we got things started. There's a whole team looking through the images as things are coming off the footprint, off the camera. We identified it. So here is a galaxy in the NGC Caliga, GC 4933, and there is the Kilonova from this object. There are many teams doing this at the same time. We actually didn't realize that someone else had seen it, had just sent out their announcement. So we were just really completely surprised that here it is. Check out NGC 4993 in this image header. So this is very, very, very fascinating. We were the second group to announce our findings, but several teams announced their results finding it within a few minutes of each other. Let's move on. Oh, and then of course we submit our own. So here's our own GCN circular that we sent out saying we found it. And here's what it looks like. Here's a time lapse over the days. You can see it fade over time. And it fades pretty quickly. And let's see. Okay, so in addition to imaging, okay, this is not, our team didn't do this, but just report what some others have done. And we kind of followed in their footsteps later on. There's this, so the Blanca Telescope is that we just looked at the results from. It's a 4-meter, there's another 4-meter telescope a couple mountaintops away called the SWOR telescope. It's very near the other telescope. It's about, I don't know, 10 kilometers or so as the condor flies. And it's also very near, you might have heard of the Gemini 10-meter telescope, so Gemini South. Here's the SWOR 4-meter telescope. In the background, about a quarter-mile away, is the Gemini South telescope. Mark Nichol took observations, spectra of this. So the spectra, okay, this is energy flux, amount of light, amount of energy flux per wavelength versus wavelength. And for spectra taken at several times throughout the 1.5 days after, 2.5 days after, 4.5 days after, and 7.5 days after the merger. And of course, it gets fainter, and so there's less energy per unit per wavelength. The shape changes a little bit. This is all this fuzz. It's really not really. It's just more or less noise. It's a noisy spectrum. It's kind of a noisy spectrum. Kilonova tend not to have, especially in the early stages in the optical, tend not to have any real features other than kind of a general background energy distribution similar to just to a warm body, a warm object. No, unlike supernova, for instance, who have big wobbles and so on in their spectra. So that's a good way to determine whether it's something that goes bang in the night is a supernova or a kilonova. We actually use that information later. Let's see. Okay, we've covered up the background. Now anyway, now on to the object that that's then as the primary feature of the talk is the GW 1908-14. That is a possible neutron star black hole merger. So preparation. So LIGO has seasons. They observe for several months or up to a year, take everything down, do maintenance, upgrades, and so on. Then they come back several months later and do another season. They've had so the black hole was discovered in their season 1. The binary neutron star that we looked at was in season 2. This one here, this is in season 3, which occurred between April 2019 and April 2020. So one thing is that the kilonova that we just looked at, that was especially bright, and it was just obvious. It's easy to find. But as technology improves, so they improve the detectors, they improve their analysis, they can see things much further, they can detect gravitational mergers from much farther away. That means that future kilonova will be typically much farther away, and even if they're all the same, even if they were all the same intrinsic brightness or had the same intrinsic energy, I mean, they'll be much more faint. If they're much further away, they'll probably also much more apparently have much fainter apparent magnitude versus absolute magnitude. In a gravitational wave sense, I guess. So 03 was going to be expected to be able to see things out to 120 megaparsecs for kilonova for neutron stars, or about 3 times the distance of that previous kilonova that we just were looking at, which is at 40 megaparsecs. So you have a much larger volume to look at, and you have a lot more transient events that you have to sift through, many supernova, to figure out which was actually the kilonova, the optical counterpart. So you want to make use. So you may still have a large set of objects after you've done your imaging and say, oh, these look like possible ones. We're not sure yet. So you want to do the spectroscopy of those objects to do the final classification. Excuse me. Let's see. Okay, let's go. So with this new one, this GW 190814. So on August 14th, 2019, the LIGO Virgo Consortium, they now have that Virgo detector, they have 3 detectors, detected GW 190814 and estimated to be at about 276 megaparsecs away, plus or minus 56 megaparsecs. They sent out a GCN circular, and actually there was some uncertainty whether it was, okay, here's what they thought it was. Here's written down what they thought it was, whether it was a neutron star black hole, something that's called the mass gap, something which has an object between 3 solar masses and 5 solar masses. They got, I think, that's too heavy for a neutron star, but too lightweight for a black hole, by theory. Or there was just a terrestrial origin detection, a truck running by on the highway or something. Binary neutron star or a black hole. At first they thought it was a neutron star or black hole. They thought maybe one of these things was in the so-called mass gap between neutron stars and black holes. And even now, there's still a little bit of controversy whether it was a neutron star or black hole or something in what's this called the mass gap. So DCAM did its search like we showed before for the binary neutron star, and they found initially 30,000 candidates to follow up. That's a whole lot of candidates to follow up after looking for things that appeared in that area but weren't in earlier images. Some of those are asteroids that were removed. Most of those were removed otherwise. A lot of these were probably going to be supernova. After doing various initial culling techniques, they were able to pare that down substantially from 3,000 to just 15 candidates. Of these 50 candidates, we observed 11 so Sahar and I and others in our group did additional follow-up with SOAR doing spectroscopy. So here is the original sky map from the LIGO Virgo Consortium, right ascension, declination, much smaller. Now if you have you have a third object and a third observatory, the area is a lot smaller. So these are this is like about 50-ish square degrees altogether. So that made it easier, and the positions of these candidates in these probability contours is shown here. Let's see. Oh, sorry. Much later, many minutes later, LIGO did a recalculation of everything, and their maps got a little bit tighter, which eliminated some of the ones on the outside, but not by too much. Observations with SOAR. Use the 4-meter telescope. Use what's called the Goodman spectrograph, an optical spectrograph. We had 11 candidates. We did initial processing and calibration and classification each night. This is very interesting. If we get something out quickly, so other people could follow up, that'd be great. What is shown here is a timeline, days since the merger, as detected by LIGO and Virgo. So there's 11 of these candidates. The red circle is the same for all of them. That's the merger event time. The blue squares are when they were identified as potential candidates, and the green are when we observed them with SOAR, did spectroscopy. Now the filled in are ones we observed that the candidate itself, the thing that blew up, that appeared to have blown up. Sometimes we're too faint, and we observe that. So we observe these all have galaxies next to them. They're associated with galaxies. Sometimes we observe what's called the host galaxy. Those are for three of the events. When the candidate itself is too faint, we observe the host galaxy itself to measure its recessional velocity, its redshift, and see if that was worked well, whether that was reasonable given what GW folks said, LIGO folks said, was the distance. And let me just show some of the some of these objects that we followed up, just a sampling. So there are 11. I'll just show you, I think, 3 or 4 here. This here is the finding chart that we've got from the dark energy camera, the DCAM observations. It's a little thumbnail. So this is what, about 30 arc seconds across. So a nice little spiral galaxy. You see the bulge and the disk, and on the outside of the disk is this object which was not there before. Now, DCAM observed several nights after the merger of this field. Observed this field many nights, several nights after this field, and I was able to create a light curve in a couple different filters. So it kind of looks like it's slightly getting brighter and then maybe getting fainter in what's called the Z band, Z filter, and can't entirely distinguish what is going on here with the one concentration I filter, but it's changing. So that's evidence of something. Okay, these 2 lower plots, we are plotting the spectrum, so the brightness or energy per unit wavelength. The spectrum that we got of the object is in the cyan, the bluish, light blue. In both these, they look different in each one because here we remove what's called the continuum, the overall shape of the spectrum in this case, but not in that case. And we also did a little bit different smoothing of the spectrum. They look a little bit different from here to here, but they are the same spectrum. So in this case, we tried comparing the spectrum with different types of supernova spectra that we had. There was a database of supernova spectra that we could compare against, and we found the best fitting ones using two different methods. And this one turned out to be what's called a type 2 supernova. A type 2 supernova is the type of which is when a very massive star reaches the end of its life, and it initially it no longer supports its core by nuclear fusion, and it collapses and explodes. Type 1 supernovas, you have a large, you have a white dwarf and another star, and that's a red giant that goes around. There's an orbit around each other, and the red giant spills gas, and you get a big explosion of the white dwarf. This is a type 2, that massive star that reaches the end of its life cycle and collapses and explodes. And yet this big feature here, we also fit against kilonova models. We don't have any real kilonova to compare against, except that one. But there are several theoretical model spectra, and you can do a lot of comparison. And here's the best one that fit best, this black line. But as we know before, unlike supernova, kilonova don't really have any features. You don't have like this big feature here in the supernova. So we can definitely say that this is a type 2 supernova, not a kilonova. This particular candidate. And the next one, okay. This case, there was something that was changing. That was brightening and fading. That appeared in the center of the nice spiral galaxy. And there's a light curve. It looks fairly constant, but it kind of drops down. substantially about 2 weeks later after the initial observations. We tried to fit supernova, match it to supernova spectra, and it's okay. You have these two large emission lines, which are very sharp. Not much really fit. There was one kind of rare type of type 1A supernova, which did sort of fit, but it's not very good. And likewise, for the kilonova, nothing really fit. And then we kind of thought, oh wait, there's something varying in the middle of a big spiral galaxy. It's probably a supermassive black hole, or what's called an active galactic nucleus, with a giant accretion disk spilling onto the black hole. So we found the spectrum of an active galactic nuclei of what's called a Seyfert-2, and yeah, it matches perfectly. So yeah, that ended up being a Seyfert-2. That didn't work out too. So then there's the case where the object, the candidate itself, was too faint, but we can still observe the galaxy. Here's the light curve of the candidate. It's very noisy. That's down to like 22.5 magnitude. It's really faint. But we were able to observe the galaxy and identify an emission line here and calculate the redshift, and it was actually much farther away than what would be expected from the gravitational wave measurement. So we were able to discount that. And there were three candidates that we had to do just this galaxy, and we were able to remove all those from the sample. Oops. Oops. Next. Okay, then there's this one. Look really closely. There's a little bit of fuzz here. And it's like a little bit brighter among that fuzz there. This is, and it has a light curve. It seems to be rising. Light curves, magnitudes. So smaller magnitudes are brighter, so it's even brighter. None of the spectra really fit too well. None of the supernova spectra fit really well. On the other hand, the observed spectrum was very, very noisy because it was such a faint object. Now here, it's a very noisy spectrum, you see, but it doesn't look like it's too bad of a fit for the kilonova, so could that be the kilonova? Well, we weren't able to resolve it from the spectrum, but actually the fact that the object was brightening over several days instead of a very rapid, less than a day brightening and then dropping off, getting faint very rapidly. This pretty much nixed the idea that this was a supernova. And actually, there's more in a companion paper of ours. Rob Morgan used some sophisticated machine learning techniques to determine that. Actually, this is probably a 96% chance this is actually a supernova, not a kilonova. So nothing turned out to be a kilonova. So none of our candidates turned out to be an optical counterpart to this merger. But we could feel not too bad because no one else found anything either. So this may just indicate that this type of merger event does not generally provide an optical counterpart, a kilonova. But it still provides some useful information for adding constraints for these types of mergers and so on. And also it prepares us for the future. Oops. Prepares us for the future. But also sort of before we go into the future, looking a little bit back, here is a plot charting basically all the stellar type black holes and neutron stars that are known, and the ones that are just these little circles in yellow, those are neutron stars detected by optical or near infrared or X-ray electromagnetic means, and purple are stellar-sized black holes, not primordial black holes or supermassive black holes, but stellar-sized black holes that were also observed, detected by stellar means. And there's only really one axis. It's solar mass, from 1 solar masses up to 200 solar masses. And then these things in the cyan or orange, those are things detected by gravitational waves through LIGO. So these are all merger events. You have actually 2 lines. You have the 2 objects that are merging and the final object. So we actually looked at, so of the ones that we looked at in today's talk, here's the black hole merger that we saw at the very beginning. Had two objects, two black holes that were 30 to 36 solar masses. They combined to form another black hole that was about 63 solar masses. Oops. Oh, sorry. I'm doing 2 things at once here. This was that binary neutron star that we saw in the middle of our talk. So it had 2 neutron stars that were about 1.2, 1.5 solar masses, and they combined to form a 2.8 solar mass final neutron star that was maybe on the edge of what's called this mass gap between 3 and 5 solar masses. So maybe there really is no mass gap. We don't know. We'll see as more data come through. And then finally, this is that last one, this GW 190814, which we just showed. So that one turned out to be a neutron, either a neutron star or something in the mass gap, plus that was about 2.6 solar masses, and something and a black hole that was 23 solar masses, and it formed something that was about 26 solar masses. Actually, okay, let's see. I'll go back a couple steps here. But anyway, there's about 50 objects here that were discovered by gravitational wave means. As we get more data, we'll have more and more. As we have more time, there'll be more and more data, and we'll be able to. Astronomers will be able to learn a lot more about these objects. So there'll be new GW observatories that will work in concert together. We mentioned the one in Washington State, the one in Louisiana. We also mentioned the one that's near Pisa, Italy. There's another one that's also been operating, but that's mainly used for testing purposes. But there's one in Japan called Kagra, which is sort of started up in this last season, but hasn't really, it's still ramping up. And there's plans for one in India to be built soon. Here, almost final slide here, is a mapping of the different gravitational wave observatories: LIGO, Virgo, Kagra, LIGO India, and the seasons. There's season 01, season 02, season 03, 04, 05, and the date line from 2015 to 2026. We finished up 03 over a year ago. Actually, the next season was supposed to start in probably around now-ish, but COVID has delayed things. So it's not, apparently the next season is supposed to start. It's supposed to start maybe in late next year. But the sensitivities will be able to look further back, further distance, detect things further away, and with more observatories coming online, you can do better at localizing them. And then, actually, that's it. That's it. Here's a nice picture of, here's the Blanca Telescope. That's where DCAM is in Chile. Here is the Milky Way and the large and small imaginary clouds. These are smaller telescopes, but perspective makes them look relatively big. It's a 0.9 meter telescope and a 1.5 meter telescope. A nice picture. And there in Chile, there's these little kind of they look like fat rabbits with long tails called biscachas, and they sit at sunset watching the sunset, sunning themselves. That's a biscacha. I took a picture at one time. And that's it. I'm not sure if anyone's still on the Zoom. I may have broken off. I think it may have broken off. But I guess any questions? Oh, you are still here. Oh, sorry. Okay. Maybe any questions from online? No? Okay.
I got a question. So that last slide for the picture.
Oops. Yes.
Is that megaparsecs increasing because of the number of observatories, or is it because the equipment's getting better, or is it because the data is piling up and we're getting a deeper view? Or is it a function of
a little bit of a combination of a couple different things?
Yeah.
One is every year they basically take about a year off in between seasons to do upgrades. So the individual instruments are getting better. And here, actually, the distances measured here are for those particular observatories. So it's this actually combines two observatories, the one in Washington and Louisiana. But it's pretty much, it's more or less independent of, these are for the detection thresholds for the individual observatories. But one thing is they're improving the equipment, improving the hardware, but also they're improving the analysis. And they've done some interesting things. They did some really interesting things between 02 and 03, which I assume they're doing even more since then to improve the analysis.
And are the models obviously being refined as well?
Yes.
Yeah, so they can give a better match on the
Yes. Oh, yes.
Question about the detector. So you said the frequency of gravity waves are on the range of a proton width?
So here you probably better to ask sonar LIGO itself, but they are using, I believe, optical lasers, so less than 1 micron.
I'm just trying to figure out.
Let's see, I kind of lose track of where a micron is in it. So these are measuring things at around 10 to minus 18 meters, but I think that's a little bit, that's another couple levels lower than smaller than a micron.
Yeah, nanometers tend to be that.
Yeah. So they have other. I mean, yeah. So it's better than the wavelength of the photons, but there are limits. I don't know. Sarah, do you remember?
Yeah, you should run.
Okay. All right. Okay, thanks.
I guess my question is, how do you measure something that's smaller than the wavelength of light using interferometry?
Yeah, it's been a while since I remember doing a physics experiment in undergraduate doing some of them. you get all these sort of interference patterns which are very fine-tuned. I don't quite remember, I'm sorry.
That's right. I was just trying to figure that out.
Yeah. Other questions? Oh, yeah.
Did you guys make it to the solar eclipse okay?
We did. It was really nice.
Where did you watch it at?
Clarksville, Tennessee. It was really hot and humid. All right. Let's see. Oh.
Would it be possible for white dwarfs to merge, and if they did it, then they also
Yeah, I would say there's no reason why they would not, why they wouldn't be able to merge. Their smaller mass, maybe their signal wouldn't be quite as strong. I don't see any reason why not. I don't know. So, have you heard anything about? No.
Would James Webb be able to contribute to this in any fashion? Because it's infrared, not near infrared.
Right. Yes, it would, but I think not in the search and discovery phase, but in the once a target has been optically identified. This James Webb has a pretty small field of view, so but it's really big mirrors, so I could look at things really well. But yeah, James will be great, I think, once you've identified which object is your kilonova.
Does it matter because it's infrared, not near infrared?
You get different. You look at different things. I think it does go a bit into the near infrared, and it's not visible, but. Oh, yeah.
At the beginning, you said about 3 solar masses went into the energy of the gravity
Yes.
waves, and not enough of that was optical light to be able to find the object, or?
Right. It was. It went all. Yeah. Since there was no sort of normal like baryonic matter around it to get compressed or show light. It basically it all either went into the black hole or into the gravitational waves. So there was really no place for it to deposit that energy into light.
Okay.
So I think yeah. Oh.
I had a question, like how often would some of these events occur in a typical galaxy?
Oh.
You get something closer, like in the Milky Way.
That's a good question. I'm not really sure. I can't really say per galaxy. I know for 03, they were thinking there were going to be, about 10 good binary black hole events and maybe 1 good binary neutron star. So there's 12 over a course of a year out to that distance. And on the other hand, you get a whole lot more supernova, at least a magnitude or more, 10 to 100 times more supernova, I think, in that volume. And I guess the rough estimate is for a normal-sized galaxy will have 1 supernova every 100 years. So very roughly, I think it'd probably every galaxy, maybe every 1,000 years, maybe. I'm just guessing. I'm not entirely guessing, but yes.
What kind of breakthroughs should we be expecting in the far future from gravitational waves?
Oh, sorry?
What kind of breakthrough are we looking at in the far future, since gravitational waves has brought us a lot of data, a lot of advancement on the study of space? Where do you see gravitational waves taking us the next decade?
Let's see. Well, one thing that's I just mentioned marginally is this measuring what's the recessional velocity, what's called the Hubble constant. Right now, you can measure the Hubble constant using the distance measured from the gravitational wave, and either statistically or if you have a kilonova, you get the redshift or the recessional velocity, and you can compare those two. Right now, you get very noisy results. But currently in cosmology, there's the supernova folks say that Hubble constant is this, plus or minus a very small amount, and the people who do cosmic microwave background say, no, it's this to a very small fraction, and they don't quite meet, they aren't quite consistent. So one thing that would be interesting is this is a completely separate way of doing things. This might be able to resolve that that tension between the two measures of the Hubble constant. I mean, it was a major feat that it was a direct first direct evidence for Einstein's theory of gravitational waves. So that there's some. It's hard. Can you think about it? Some other things right off? Yeah, those are
Well, it will go in space to measure the gravitational wave with
Lisa. Oh yeah.
Yeah.
So.
There is a huge future.
Oh yeah.
for space.
Yeah, technologically, there's a lot of the sensitivity is how long those baselines are on the observatory. So there's this is LIGO. There's a plan to put something in space called LISA, which is a very large, very large. I'm not sure. It's like they're measuring the lengths on what, AE scales or something. That's a couple of decades away, probably. Oh, thanks. Oh, yes. Maybe back there first.
Is the strength of the gravitational wave dissipating our distance, so it's easier to detect the closer ones versus the farther ones?
Yeah, it basically goes like light. It goes like a inverse square law. Oh yes.
This one's sort of related to that question. So two black holes merge, given the amount of energy that's released in the wave energy. If you were relatively close to this, I don't know, light year, 2 light years, would you feel it? Would it rip you apart?
That's a good question. That's a solar mass, or 3 solar masses of energy.
It's a lot.
Over a very short period, over like a few seconds. Yeah, if we're too close, it would not be good. I don't have the numbers off.
That you would like to be close.
Yeah, I haven't thought about it beyond that, but yeah, I don't want to be too close to one of these things. Yeah.
So in the simulations you showed of the stars coming together, or the objects coming together, the stars on the periphery were being whipped back and forth. Is that an optical illusion, or is that actually happening? Are they actually being pulled back and forth?
Oh, well, the stars themselves are just the light. So it's the negative light from the gravity. The gravity's. Oh yeah, I should. Let's see. I should do it also for the people online too. Find that.
You're on the Zoom.
Yeah, I'm doing the Zoom. I want to get the Zoom ones to, yeah, since they're kind of neglected a little bit. I'll get them. Okay. Oh, here we. Oops. Oh, but too far. No. Or did I didn't go too far. It was after this, and this, and this, and there we are. Yes. So yeah, this is just this is just in some sense an optical illusion. It's oh yes.
The gravitational wave, and there is also the lensing effect that's happening. So what you see is lens plus gravitational wave.
Yes. So yeah, mass acts like a lens, and so you're seeing the lensing phenomenon. The stuff behind being like if you had a big mirror or a big glass lens between you and behind.
So actually, perfect transition here to this website. I pulled it up as well on my phone. But who runs this project? Washington State University, or all those universities?
Oh, for that particular simulation, yeah, it was a group effort. Okay. And they're probably they must be associated. Yeah. Very pretty though, and the other one too, which is NASA Goddard. But yeah, here also you see it's the lensing of the mass of the background stars. The stars themselves are not being moved. It's just from our perspective, we see the lensing effect.
They're closer, are they being exactly?
I guess on how close, if they're in the same, solar system, yeah, they'll be affected. I think if they were like between the sun and Alpha Centauri, the effect would be pretty well. Getting back to the other question about three solar masses being spilled out into the gravitational waves, I don't know about that, but I don't know. I haven't really thought about that. Okay. Any other questions online? Okay.
Thank you very much.
Thank you.